My name is Daniel from Upstream Tech, and thanks for joining our conversation today. We're going to focus on, as you probably all know, water supply forecasts, and in particular, how we can make better water supply forecasts in a world that is changing. So you probably just got a notification. We'll be recording this session, and the idea is that we'll chat for about 25 minutes or so, and then open it up for discussion and any questions that you have. So before we dive into anything technical or really looking at forecasts or research, I think it's helpful to anchor this conversation in why forecasting matters and the role that forecasting plays, especially in places like the US West. So the first thing to remember is that in a lot of places like the US West that are driven by seasonal runoff and that have a lot of snow, these water supplies are really important for everything from drinking water for communities to growing the plants that we rely on, producing energy, and then creating a healthy ecosystem. Beyond that, though, most of the construction that happened over the last 150 years and built the US West as we know it today happened during a period that was unusually wet. And so even beyond climate change, we would expect sort of a reversion to normal that would be not as wet as what we came to rely on when we built the communities that we're living in today. And beyond that, though, the climate is changing as well. And so we're seeing much more frequent extreme conditions. We're seeing years that are simultaneously wet and dry and hot and cold, but that are moving away from what we are used to. So you have sort of this double bind where water is less reliable than it used to be, but we need each drop even more than ever, and it's harder to forecast that. So that's going to be the focus of today's conversation. Just a quick overview of what we're going to run through today. You're going to hear from me. As I mentioned, my name is Daniel Palmer, and my colleague Laura Reed, who is our product manager on the HydroForecast product. And we're going to talk through the traditional approach to forecasting seasonal water supply, and then look at some recent research that we've conducted that shows promise for improving the accuracy of those forecasts, and then move beyond just the research to see what these forecasts actually look like live in a place like California, and then talk through some of the lessons that we've learned through this research and the next steps that we see coming up. Feel free, please, to drop any questions as we go through. Just to keep everything clear, we'll probably run through our presentation and then open up for discussion. But I know we've got a variety of folks on the call who have quite a bit of experience doing seasonal forecasting and who live in places where seasonal water supply is super important. So we're eager to hear your perspective and feedback and ideas as we go through this. As a quick background on who we are, why we care about this topic, and why we're here today, we're joining you from a company called Upstream Tech. So we're a public benefit corporation, and our main focus is on building software that helps folks, especially decision makers who are relying on environmental data, have the best information possible. Our team is split about 50-50 between domain experts in things like water resource management, hydrology, and environmental science, and then technologists. And you'll see that sort of mixed blended team approach coming through in some of the methodologies that we talk about in the research today. So right now we work with a couple dozen organizations. We're forecasting for drainage area about the size of the country of Turkey or France across a variety of different offerings that we're using. And we're live on 4 continents at the moment, working with a variety of hydropower producers, governments, and organizations focused on conservation. So as we talk through our research today, I think it's helpful context to understand what we're doing this research in. So if you don't already know us, one of our main products is called HydroForecast. And at its core, it is a system to help predict how much water will be coming into a point at different times in the future. And so as we look at the research that we've conducted recently, we have operationalized all of that through HydroForecast. And I won't go too far into the details of what HydroForecast is, but But sort of the things to know about it are that we use a somewhat unique approach that we call theory-guided machine learning that aims to combine both the benefits of technology and machine learning with domain expertise in hydrology. And one thing that's really been beneficial about having this system is that it's set up in a way that allows us to bring new data sources into operations really quickly. So we can experiment on whether there are things that improve our forecasts and see what that looks like live in a relatively quick period of time. HydroForecast works across a range of time horizons, from predicting things in near real time all the way out to looking multiple decades into the future and seeing how different climate scenarios might affect flows. But we'll be focusing today, as mentioned, on seasonal water supply, so looking multiple months ahead. Cool. So the reason that we're all here is to talk about seasonal forecasting. And I wanted to first set the groundwork with talking through the traditional approach to forecasting water supply multiple months into the future. So the traditional approach is to look at the current conditions in a basin. So for instance, you have a valley or a basin that is getting a lot of snow, you would look at the snowpack that's on the ground, current flows and storage. And then the question is, okay, we don't know what the temperature or the precipitation for the rest of this year will look like, but what would our flows look like if any of the past years had happened? And so you develop what are called traces, looking at each year in your historic record. That might be 40 years, could be 80 years. And you apply each of those years to the current conditions. And then that produces for you a stream flow prediction. And when you plot out that full range of results, you get a distribution that shows, okay, what would the flows look like this year if it were an average year? What would it look like if it were a historically wet or a historically dry year? This is generally the best methodology, and it's one of the most consistently used methods throughout the water resource management world. It's helpful because it's both able often to provide you some insight into what flows might look like, but it's also a clear methodology, and it allows folks to understand, okay, how does this year compare analogously to prior years? That said, there are a few limitations. And so what you're seeing here are quotes from some recent research around limitations in this traditional approach to water supply forecasting. The first is that some of the old rules of thumb that we might have relied on of relationships between things like, okay, there is this much snowpack in the basin, so we can expect these flows, are breaking down during extreme conditions. The second is that what I just showed you assumes that each of the prior years in your record is equally likely to happen this year and in future years, which we know isn't true. We know that those climate conditions are not actually stationary, and that there are some historic years that are more or less similar to what we might see this year. And the third is that there's been a lot of improvement recently in climate forecast and climate data that looks forward multiple months. And so if you don't take advantage of that, you are leaving potential insights on the table. So what we're going to talk through, and I'll pass this over to Laura in just a second to talk about some experiments that we've recently conducted, are going to fall into each of these three categories. So the first is, are there ways to better account for all of the different inputs and processes that are happening between precipitation falling in a basin and that water showing up or not showing up as a flow? The second is identifying if there are ways to understand which years of the past are more likely to be similar to this year. And then the third is incorporating that subseasonal to seasonal data and forecasts. So I'll pass it off to Laura now to talk a little bit about some of the recent research that we've conducted.
Great, thanks, Daniel. You go to the next slide. Great, so you gave a nice overview of the philosophy that we take to hydrologic modeling, and just to dig in that a little bit deeper, basically a theory-guided machine learning approach to us means we build our model using a statistical neural network And the way that we conduct that model building and the way that we train, validate, and produce that model is constrained and built toward how we understand hydrology. So hydrologic theory, hydrologic processes are built into our approach exclusively. And what that does is, and what that means is that we can make a model that can leverage all of the advanced computing and data that's out there in a way that allows us to scale a model that's unified and also can see things outside of the record in which it was trained. So normally most hydrology, at least up until this point, is a sort of a basin by basin approach. And what we've tried to do here is build something that can actually take advantage of lots of different data in a bigger way so that we aren't building that basin by basin approach. So really what that means is we take all these little dots or points on this map show our core model training sites. And what we do there is we take the historical records, we take the best weather data from history, satellite observations. So we're able to see, the model sees what's happening on the landscape and how that landscape is changing. And then specific drainage basin characteristics like soil types, land use, all of that. And also specific snow products that can help the model learn how to partition precipitation that's coming down into snowpack. And we train that model over hundreds of basins that you see on this map. And what that does is it allows the model to build a really core understanding of hydrologic process. And then it also allows the model to, if you're going to make a prediction in a new basin, take that learning and apply it there. And so if the model has seen an extreme event somewhere else, it can understand how to interpret that in a way that's a bit more advanced than if you were to set up a traditional model. And so that's how we sort of scale our approach, and we take this approach on all of the different horizons that we offer forecasts. And so here I'll talk about some of the ways that we've applied this to the seasonal water supply forecast. And Daniel, if you go to the next slide. So here's an example of what our a customer's seasonal forecast. This is a 90-day forecast. You'll notice a couple things. We have a probabilistic approach. So the neural network that we use is actually predicting all the quantiles of flow, and folks can use that if they are making risk-based decisions or taking these predictions and putting them into a downstream model, like a systems model, et cetera. So we have a mean, that's that dark line there, and I'll talk a little bit about how we build this distribution in this model. So if you go to the next slide, we start out with something that's pretty similar to what Daniel was describing, where we have traces. And the reason that we did this was, for Daniel already said this, but it's a familiar approach. Folks can look back in their memory and say, oh, I remember that flood of 1999. I remember that drought of 2017. And so we tell the model, all right, condition yourself on the last 10 to 12 months of the basin conditions today. And then starting from today, take the last 40 years of weather and go take those traces and tell me what could happen in the future. Now, for reasons we've already discussed, and I'm sure y'all already know about, using past weather to predict the future is limiting, and it's not really holding up in certain places, given climate change and the extreme events that we are experiencing in certain places. So what we've done on top of that, and where we're spending a bulk of our research effort right now, is how to help the model say, you know what, I know not all of those years in the past are equally likely to happen. So what can I pull from weather forecasts, climate indices that can actually help the model be smart about choosing the years that these realizations could turn out to be? And so we call that our similar years, or similarity. And what you see below there is what we do is we take different inputs, and I'll talk about these on the next slide, of what could help the model learn what this year could look like compared to all those other years in its history. So here we have a subset of years, and from that subset, we build our mean. And so the mean of our forecast, that dark blue line, is coming from that selection of similar years. If you go to the next slide. So what have we tested, and where has that gotten us? we've tested a few things. So NOAA's GEF's weather forecast goes out 35 days. And so if we put that into the model as an input and say, here, model, here's what the weather is going to look like. So we're incorporating forecast information along with those historical weather traces. We've actually seen probably the best widespread improvement in skill using GEFs. We've seen that in both North America and also in Australia. There's a couple of other weather forecasts that we can put into the mix as well. ECMWF has an extended forecast, but of course, none of those are going out 90 days a year. And so that's another place that we're looking to expand, is how can we get more forecast information that has signal in it into the model. Climate indices is another place. So a lot of the research and folks that I've read about and heard talks from, INSO has been a big predictor. I've also heard, and we've experienced the same thing, where that gives you mixed results. And so it can be really powerful in certain years and in certain places. We've seen pretty mixed results applying that in different places in the US. And then we've also tested out some proprietary weather forecasts and seen mixed results as well, but we'll continue to develop on these fronts. So let's dive into some actual examples.
Yeah, so thanks, Laura. That was really helpful, I think, for talking through some of the specifics of what we've looked at. One thing that we're really focused on is not just conducting research, but always translating that into operations. And so as one example of that, we have created a variety of different models that we've been experimenting with. We took one of those models and set it up live for California. And what we're going to talk through in a second is looking at how that model has performed over the past 2 years. So if you had been a water resource manager in California over the last 2 years, what would you have seen from one of these HydroForecast models? So the way that we wanted to conduct this evaluation was to understand, okay, what sources are folks relying on right now for their water supply forecasting? And are there ways that we can supplement that information or make even more accurate forecasts? And so the general sort of canonical approach for forecasting in California, the resource that everyone relies on, is the Department of Water Resources puts out a document called the Bulletin 120 and the Water Supply Index. So you can see an example of that on the right here, but generally what it looks at is across really important points in the state, what are flows projected to be for each of the upcoming months. So you can see the rows here of places like Lake Oroville, and the columns of what is the inflow expected to be for that month. This is really relied upon across the state. So if we're able to find ways where we can improve upon that, that would be really promising for helping folks within the state make better decisions. The way that we ran this performance benchmark was to set up a forecast that was looking 90 days ahead, and then compare that to the Bulletin 120 and the Water Supply Index predictions at 5 of the state's largest reservoirs. So we looked at essentially 3 forecasts. We looked at forecasts issued on the 1st of April for both this year and last year of those full months of April, May, and June. And then, because knowing potential flows earlier in the year is also important, we looked at what were the flows for April as predicted in early February of this year. Overall, the results were really encouraging. So the high-level takeaway is that this HydroForecast seasonal model that we evaluated was able to improve accuracy in 12 of those 15 forecasts. So we'll dive into that a little bit. First, starting with looking at predictions made in February for this April's inflow. So just to quickly show you what you're looking at here, this is a chart showing relative forecast performance of forecasts issued in the beginning of February for total inflow volume in April of 2022. And these are 5 of the largest reservoirs across the state. What you're seeing with this darkest line is the observations, what actually happened. So a perfect forecast would look exactly identical to this black line. The two lines in the middle are HydroForecast's predictions, and then the DWR forecast. And then on the right, you see the long-term average. So if you take the last 40 years and looked at the average April flows at that location, what you would get. So the main takeaway here is really encouraging results from this R&D that we've conducted. You can see at 4 of the 5 sites, a pretty clear improvement of HydroForecast identifying deviations away from the long-term average that are much closer to the actual observed flows. And it's not just that the forecasts are accurate, but it's that they're picking up directionally that change from the historical average, and that they're getting the magnitude more accurate than an alternative forecasting approach. We'll look now just at a couple of different sites across the state. So this was overall the best performing forecast that was produced during this evaluation. And it's looking at Millerton Reservoir, which again is one of the large and important reservoirs across the state, and looking at the forecast for total volume of inflow between April and June. So that really important period when all of the water, much of the water that's going to be coming into Millerton over the course of the year, melts from the snowpack and comes into the reservoir. And so what you're seeing here is that HydroForecast was really able to accurately dial in to within 1% of what flows ended up being during that period. If you look at that same site in 2021, there's a similar story. You can see both forecasting methods picked up on the fact that it was going to be a low year and picked up on that deviation from the long-term average. But some of this research that we've conducted enabled the model to more accurately pull down a little bit on the prediction closer towards what was actually observed. Looking at New Melones, another really important reservoir in the state in this past year, 2022. You can see again, sort of the story across all of this is unfortunately a story of drought and of low years. You can see both the DWR forecast and HydroForecast predicting that it would be a significantly lower than average year. In this case, HydroForecast was less bullish than the DWR forecast on how much water would come through. In particular, looking here, if you look at the April and May flows, that thinking they were going to be very low, and they did end up being quite a bit low. And then just the last example that I'll show is New Melones as well in 2021. And so similar story, you see the traditional forecasting methodology picking up on the case that it was going to be a dry year, but some of this research that Laura talked through really helping HydroForecast pick up more accurately on just how severe that change was going to be and just how dry of a year it would be. So stepping back a bit, that's one example of one of the models that we have tested. So let's see what we can learn from that, talk a little bit about what's next. And then I see there are some questions coming through in the chat. So happy to shift over to that in just a second. From a high level, I think the main things that we saw are a lot of promise and potential from this research, also a lot of room for improvement. We'd love to see that teal line always being right next to that black line, and especially when it's so important to understand how much water is available, there's still a long way to go there, but we think a lot of this is really promising. Another takeaway for us is just that this ability to translate from conducting research and experiments into actually seeing how the model did in real life really helps us understand which methods are driving skill and which methods are worthwhile, and then iterate on that. So being able to see those specific sites of, okay, here's how the model did at this location is just really important and really valuable when you're trying to conduct a variety of different experiments. That said, we do think that there's still more research needed to understand which of the methods are most valuable. And as Laura mentioned, we've looked at this across different circumstances. So identifying what drives skill in which circumstances is a really important, outstanding question for us. For the coming period, there are a couple areas where we really see room for improvement that we want to focus on. So if you go back to sort of those 3 points that we talked about early on, that first one of incorporating more robust data and looking across a broader data set has been really promising. So let's look at what can we do around better incorporating weather forecasts and similarity. One thing that we've seen with the weather forecasts is that anything beyond about a month into the future, the forecasts don't have very much skill. And so understanding how you can best incorporate forecasts without relying on them at points where they're not telling you that much is an important question, and seeing if there are ways to improve that skill further. The second is that, especially in places like the US West, extreme events like atmospheric rivers are just really crucial to making or breaking a year. Despite being in drought, last October and November were some of the wettest on record in California. So if there are ways that forecasts can identify and quantify those anomalies earlier, that's going to be really important for improving how well the forecasts do overall. A second main focus is going back to this topic of similarity. So one thing that we've seen is there is still potential for better selecting which years to use as the similar years that we're calculating the mean based off of, but recognizing that when you're selecting just from a historic record, that's a limitation if you have future years or the current year that is entirely outside of your record. I won't go too far into it, but just some research that we've conducted around similarity is shown in this chart on the right. And so generally what you're looking at is across different forecasting similarity selection approaches, what is the total error of the forecast if you plot it year over year over year? And so this blue line here shows if we were able to identify the years that had the most similar discharge to this year, so the most similar overall flows, what would the error of our forecast look like? So that's sort of the theoretical limit of improving similarity selection. And so what we're focused on going forward is identifying other methodologies that can help bring our selection approach down to this sort of theoretical maximum of similarity skill, and then seeing if there are other ways beyond just similarity selection to reduce forecast error overall. And so in particular, what that's looking like for us over the next coming months is finding ways to improve our similarity selection approaches. A couple inputs that we think show a lot of promise that we're going to dig further into are using salinity and sea surface temperature as potential methods for identifying which historical years might be most similar to this one. And then also using things like synthetic weather traces to create examples that are outside the historic record that we're using that include more extremes so that we're not just reliant on that current record. We also want to look through, okay, of these different experiments that we have tried, which ones are consistently showing the most improvement, and then be able to scale that into a model that works especially well globally. And all of this is happening in tandem with us deploying live operational forecasts for our partners. And so one priority is, as we continue to bring on new partners, understanding how our models perform with them in different places, and then really refining and iterating to continue to make better operational models for all of our existing users. So if that's a topic that you're focused on, we'd love to partner with you. We'd love to better understand coming out of this conversation, what are areas that are big focuses for you? What questions do you have? And how might we be able to work together to actually deploy some of these experiments going forward? So with that, we'd love to open it up to any conversation. I see a few questions coming through in the chat. If you have any questions or thoughts, feel free to drop them in the chat, or you can reach out to either Laura or I at the contact information listed here. Thanks, everyone. All right, looking at questions. So the first one says, I'm familiar with various statistical and process-based models. How does our model differ from these beyond just combining approaches? Laura, do you want to chat through that a little bit?
Sure, yeah, it's a great question. So if you recall that map I showed of all of the basins with the points on it, one of the things we do different than just saying, hey, statistical model, like here are the inputs to pay attention to, is building that core model that is across many, many different sites. And the power that gives us is we can use transfer learning to then go into a new basin and actually have a really strong base prediction. And then after that, use specific local information like, we pull in all of the inputs for the basin and also the gauge observations if available, and make an even stronger prediction. And we've tested this. Actually, we took our North American core model and we have some forecasts running in Central Africa. And we took that model and made the predictions there. And it was actually pretty darn good out of the box. And so that goes to show that the way that we are approaching actually building the model is more than just saying, let's be in the middle of the spectrum of process and statistics. Happy to go into that further here or somewhere else too. It looks like the next one is data inputs. Great question. So as we all know, at different horizons, there are different things that influence hydrology, but the core things that are true across all of our models and horizons are, we use weather forecast data. So we're using a variety of NOAA sources, GEFS, GFS, ECMWF, high res. We have the extended as well. The HER forecast, which is a high resolution 48-hour forecast. It can get convection where we need that. And then on the climate scale, we're using like CMIP, which are the global climate models that are predicting precip and temperature all the way out. We also are pulling in MODIS satellite data for snow cover. So that's to give not depth, but coverage of snow, and the NDVI, so the vegetation index. And it's kind of interesting. Our model is seeing how those interplay. So when there's a lot of snow on the ground, there's low NDVI or low vegetation. And then as the snow's melting, all of that moisture is going into the soils, things are greening up. And that actually helps our model, along with like temperature and how things are warming and cooling, really understand hydrology. Excuse me. We also pull in SWE, so snow water equivalent, from SNODAS. And then, like I said, a bunch of static data sets that describe the land surface. And then if we have gauges, we can use those and assimilate those in real time in our model.
Yeah, awesome. And so, yeah, for anyone who's maybe more of a lay listener here, abstracting that up to just the general categories of data inputs. So we have traditional data sets that are describing the basin. And then in real time, the model is being updated with a variety of the best weather forecasts that are available. It's looking at each of those and trying to understand what's best in the basin. And then looking at satellite images every day that are showing real-time conditions of what's happening in the basin. And whenever there is in situ data, the model is able to sort of assimilate itself back to reflect on what's actually happening with the flows in real time. And that, I think, leads pretty well into another question that we've got on, can we do these forecasts remotely for anywhere? What human intervention is needed, and do we need in situ sensors? And so that's a great question. If you recall back to Laura's discussion of the way that we've set our model up, so rather than just doing a sort of model for a single basin and calibrating it for that, one unique thing about HydroForecast is that it's already been trained across hundreds of different basins. And almost all of the data sources that we use are globally available. So what that means is that, yes, you can set up a forecast point using HydroForecast anywhere on Earth. And even if there is no gauge in the area or any in situ sensors, the model can perform well. We validated that in Oceania, in Africa, as well as a couple different places across the US and in Europe. And so for us, that's really promising, because beyond looking at, how can we marginally improve skill at places that already have sophisticated forecasts, being able to provide earlier flood detection or drought detection forecasts in places that don't have any high quality data on the ground is a really important challenge. And I think one that going forward will be quite a bit more of a focus for folks. So Laura, I don't know if you have anything to add on that point as well.
Yeah, I would just say the short answer is no, we don't need in situ sensors. It's obviously helpful for our model and for us to understand how the forecasts are doing, but we are able to deploy anywhere because the sources that we use are global sources.
Great. I just saw a quick follow-up to that around soil moisture data and having very high resolution satellite info. Laura, could you maybe speak to how the model approaches soil moisture?
Yeah, so the model is tracking soil states just like a physical model would, just in a fundamentally different way. Instead of prescribing parameters with equations, it's learning that through the inputs that we're giving it. And we can actually diagnose that by looking inside the model. So the model is learning those sort of shallow groundwater and soil absorption parameters in a different way. And we see that with how the model is able to melt and accumulate snow in certain places. And then also in places where we don't have snow, being able to say that this is going to contribute to runoff correctly or infiltrate the water into the ground. Good question.
Awesome, thanks. And then maybe Laura, you could talk a little bit about how we're subsetting historical meteorology into the similar year traces.
Yeah, and there's a lot more to talk about there, a lot of research to do, but the basic thing is that we're taking weather forecasts. So let's say NOAA's GEFS looks out over the next 35 days and it says, all right, we're going to have X amount of rain, and we're taking the mean of that forecast. Then we can go look at the years that we have available from the historical meteorology, and we can say which years are looking like that over the next 10, 20, 35 days, because we're making a prediction every 10 days. And so the model is interpreting what those forecasts are saying and then helping us pick the years that look the most similar to that. And then we can also do that with other things like climate index, INSO thing, other signals like that.
Perfect, awesome. I see a question here about the Airborne Snow Observatory work in California. So it's a great question. That's another area that I think is really promising for improving forecasting in California. For folks that aren't aware, this is a series of flights that are being run throughout each winter that help give a more accurate understanding of how much snowpack and snow water equivalent are in each of these really important basins. We're very much looking at different ways to incorporate ASO data into our forecasts. A few of the sort of things that we're thinking about are, one, how does that get incorporated into other data sources that we might already be using? So is there a way to improve the upstream forecasts, the forecasts that come before us, not the upstream tech forecasts, that would enable us to be bringing in the best data that's available? And so that's both ASO as well as some work that's happening at Scripps with a group called CW3E that's trying to improve forecasting for atmospheric rivers and ridging. And then with bringing ASO directly into our forecasts, I think one thing that we've been wrestling with recently is trying to understand, okay, so the main inputs to our model are updated, let's say, twice a day, and every day, twice a day, you get those updates. And so the model has learned really well how to handle those and how to incorporate those going forward. And when you have flights that happen at irregular times that are not sort of in that consistency of the relationships that the model knows how to handle, understanding the best way to bring those in and assimilate them with the rest of the data that you're looking at, I think is very much an open research question. And so that's one thing that's been top of our mind as we've been thinking about the ASO data. Laura, do you have any other thoughts on ASO or some of the new meteorological products that can help improve forecasting?
Yeah, I think that sums it up pretty well. I'd just say I think the direct insertion of the ASO data is something I've heard lots of folks talk about, like how, because even not in a model just like ours, but even in a more traditional or physical model, that's something that you have to calibrate and figure out how to incorporate in a way that can help the model and not just make an abrupt change. So we're really interested to learn more about how we can do that too.
Great, awesome. We've got a question here on collaborating in South Asia on Himalayan glaciers. And yeah, please reach out to us. We'd love to chat. We have recently been doing a lot of research on glaciers in particular, especially at the long-term scale of understanding what that looks like for not just glacial mass balance, but how that actually affects stream flow. So we'd love to chat further. Thanks for asking the question. And it looks like a follow-up question on that around long-term climate scenarios. So yeah, the short answer is yes, that's another big area of focus right now is, everything that we've just talked about so far in this webinar has been, okay, can you make predictions that are multiple months into the future, more accurate than what's available out there? And then beyond that, a lot of the research and the operations that we've already deployed so far show promise for being able to look further into the future out multiple decades. And so we have, it's a fortuitous question, we've actually recently launched an offering that's focused specifically on looking at different climate scenarios and understanding, okay, given the conditions that are predicted then, what would flows look like at this area of interest? And so we know from some validation that we've done in our short-term model that HydroForecast is one of, if not the best tools available to be able to translate different things like precipitation and temperature into actual expected runoff. And so by bringing in the best available long-term climate forecasts into HydroForecast, we're able to show what are a range of potential scenarios in this basin under different climate emissions scenarios. Awesome. Well, I think that wraps up everything we've gotten so far. As I mentioned, we'd really love to better understand what work other folks are doing. We know this is a place that's both really important and ripe for a lot of innovation at the moment. So if you're interested in chatting, please do reach out. We'd love to chat. I'm sure folks are taking the Thanksgiving break soon. So happy to reconnect after that if that's most convenient for everyone. And we'll record this as well. So if you have other colleagues or folks who would like to check this out, we'll send that around in just a couple of days. But thanks again for joining, and we hope to talk to all of you soon.